Okay, so hello and welcome back. So the rest of the story of limits is just a couple of illustrations, and these illustrations basically what they do, they illustrate how you calculate the limit of basically some typical functions. And then we will talk about some algebra of limits. So suppose that we have some functions, for example, something like f of x. F of x is equal to x plus 10. And what we want to do, we want to find the limit of f of x when x tends to 5. So, and of course, since x is tending to 5, you need to find the values of f of x very close to x is equal to 5, meaning that you need to get very close to 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then your function goes through these 2 points. So this is the graph of the function f of x is equal to x plus 10. Just to make sure that I haven't made any mistakes, because sometimes these functions are tricky. If y is equal to x plus 10. And as you can see, the function goes, y is equal to x plus 10. The function goes through basically this point 10 over here and this point negative 10 over here on the x-axis and the y-axis. So this is point 10 and this is negative 10. Now at x is equal to 5, you can see that the function is going through the expected value of the function at this point is 1, 2, 3, 4, and 5. It's this point over here, which corresponds to this point, which is 1, 2, 3, 4, and 5. This is 15. Meaning that at x is equal to 5, the value of the function is 15, 5, 15. Meaning that as I get closer and closer to 5 from the right, the function is approaching this point 5, 15, and as I approach the point x is equal to 5 from the left, again the function is approaching the same point 5, 15. So that must be the limit of the function at x is equal to 5, or when x tends to 5. But of course you can always do a create some table over here, and suppose that I take this point as x exactly equal to 5, and then I can approach x from the left on this side of the x, and I can approach x is equal to and I can approach x is equal to 5 from the right, from this side. So for example, I can go for 4.995, I can go for 4.99, I can go for 4.95, and I can go for example 4.9. So the difference between 4.9 and 5 is 1/10 of a unit. This is 500th of a unit. This is 1/100th of a unit, and this is basically 5,000. For over here, the difference is 5,000th of a unit. And then I can approach x from the right. I can go for 5.001. I can go for 5.01, and I can go for 5.1. I can go for 5.1. And since the value of the function at any point is x plus 10, the value of the function at this point becomes 15.001, 15.01, and 15.1. The value of the function here becomes 14.995, 14.99, 14.95, and 14.9. Now you can see that when I get very close to 5 from the right, the value of the function is very close to 15. When I get very close to 5 from the left, the value of the function is very close to 15. That means that what that means is that I can write the limit of f of x when x tends to 5 from the right is 15, and the limit of f of x when x tends to 5 from the left is equal to 15. So I can say that the limit of f of x when x tends to 5 from the right is equal to the limit of f of x when x tends to 5 from the left is equal to the limit of f of x when x tends to 5 is equal to 15. So again, what's important here is that from this table, what we deduce, and deduce is the right word to use here. What we deduce is that the value of f of x at x is equal to 5. I do not really know if it is really 15. I know that the value of f of x at x is equal to 5 is some value between 14.995 and 15.001. Of course, provided that nothing dramatic or unusual unusual happens between x is equal to 4.995 and x is equal to 5.001. Provided that that's the case, then I can deduce that the value of f of x at x is equal to 5 is some value between 14.995 and 15.001. So now it's reasonable to assume that the value of f of x at x is equal to 5 as dictated by the numbers to the left of 5 is 15. As dictated by the numbers to the left of 5 is equal to 15. And similarly, when x approaches 5 from the right, f of x should be taking the value 15, for which you can write this equation up here. And so we can say that it is likely, you need to pay attention to the words that I'm using. It is likely that the left-hand limit of f of x, which is this limit, and the right-hand limit of f of x, which is this limit, are both equal to 15. It is likely. And these are all in all likelihood and assumption and things like that. Therefore you can say that the limit of f of x when x tends to 5 from the right is equal to the limit of f of x when x tends to 5 from the left is equal to the limit of f of x when x tends to 5 is equal to 15. And of course you can check this, the conclusion that we came to. You can check this on the graph of the function. You can see that as you get closer to 5 from the left or from the right, the function is tending towards this point, which is 5, 15, which is the value of the function at that point x is equal to 5. And of course, over here you can also observe that again, f of 5 is actually equal to 15. And the limit of the function, if I assume that all of my assumptions are right, then I can say that the limit of f of x as x tends to 5 is actually equal to f of 5, which is equal to 15. That is basically the whole assumption, the whole thing over here. So now this is one complete illustration showing basically, for example, how you go about finding the limit of some function. For example, f of x is equal to x plus 10. As another illustration, suppose that you have some function, for example, f of x is equal to x cubed. You have some function f of x is equal to x cubed. And you want to, basically you want to find the limit of this function, the limit of f of x when x tends to 1. That's what you want to calculate. So logically what I need to do is get close to 1 from the right or left, meaning that I can create a table over here, or first let me do a graph for this function. Let me do a graph for this function. The graph of this function is basically like this. The graph looks something like this. So this is y and this is x. And this point over here, these are some points on the graph of the function. Now, so that here is your graph, and then you can also do a simple table for this function. So suppose that this is, for example, the x and this is f of x, and you want to get closer to x is equal to 1. So I put x is equal to 1 somewhere over here in the middle, x is equal to 1, and then I have to get closer to x is equal to 1 from the right and from the left. So the values that are available in the book, I don't want to be calculating. Basically, it's not easy I mean, it's not convenient really to cube, to raise some numbers, like for example 0.999 to the third power. So I'm just going to use the values that have been calculated in the book. So for example, this is one value for x, which is very close to 1 from the left. Another value for x, which is a little bit farther away. And this is some value which is a little bit farther away. On the other side, you will have 1.001. Then you have another value which is 1.01. And then you have 1.1. Now the value of this function at this point becomes 1.003003001. At this point you will get the value 1.030301. At this point you will get 1.331. At this point you will get a value 0.997002999. Of course it's supposed to be not here. I guess I will rewrite this part. So that the value over here is 0.997002999. For this input, the output is 0.970299, 9702999, or 99. And over here is 0.729. So as you can see, as I am getting closer to, basically, as I'm getting closer to 1, from the right, the value of the function is tending towards 1. And that is, of course, this point over here, which is 1, 1. As I'm getting closer to 1 from the left, you can see that the value of the function is tending towards the same value, 0.997, and so on and so forth. So from this table, we deduce that the value of f of x at x is equal to 1. We can say that we deduce that the value of f of x at x is equal to 1 must be some value between 0.997002999 and 1.00300001, assuming that nothing dramatic happens between these two inputs, between these 2 points over here. assuming that nothing dramatic happens between x is equal to 0.999 and x is equal to 1.001. Assuming, having basically making that assumption, then if that's the case, then you can conclude that, or then you can deduce that the value of the function at x is equal to 1 is between these two values. Okay. Now, now it's reasonable to assume that the value of the, and you need to pay attention to basically the language that I'm using here. I'm saying that it's reasonable to assume that the value of f of x at x is equal to 1, as dictated by the numbers to the left of 1, as dictated by these numbers, that value is 1. So I can write the limit of f of x when x tends to 1 from the left is equal to 1. And similarly when x approaches 1 from the right, f of x should be taking the value 1, meaning that the limit of f of x when x tends to 1 from the right is equal to 1. So hence it is likely that the left-hand limit and the right-hand limit of f of x are both equal to 1. It is likely. I can say that hence it is likely that the limit of f of x when x tends to 1 from the left is equal to the limit of f of x when x tends to 1 from the right, and that is equal to 1, which is equal to the limit of f of x when x tends to 1. And of course, the same thing, basically the same conclusion, when we say that the limit of f of x basically and you can say that, and this is also basically this is also important that you say that this conclusion is somewhat strengthened by seeing the graph of this function, function which is basically given over here. But now you can see that on the graph of this function, so basically what I'm looking for here is I'm looking for the limit of the function as x tends to 1, and Okay, so now there is a lot, everything that we said over here about this illustration, we said that basically, for example, over here, we said that, for example, we can deduce that, for example, the value of f of x is between these two values if we assume that nothing dramatic happens between these two values, for example, which is something that needs to be taken care of later. I mean, the way that we are taking the limit of these functions is not that precise. I mean, it's not exactly defined, meaning that over here I'm making an assumption that nothing dramatic happens between, for example, these two values of x, which is of course not a safe assumption to make, because anything could happen between these two values of x. And so, but of course these, for example, this point will be taken care of later once we define limits. That will be taken care of. And moreover, and so basically then again we said that it's reasonable to assume that the value of f of x at x is equal to 1 as dictated by the numbers to the left of 1 is equal to 1. We said that it's reasonable to assume that the value of f of x at x is equal to 1 is as dictated by these numbers to the left of 1 is equal to 1, meaning that these numbers are approaching some numbers 0.997002999 and so on and so forth. So based on that, we deduced or we assume that the value of f of x at x is equal to 1 is basically this value over here. So we are basically taking things a little bit loosely. I mean, but of course, limits are not just a bunch of assumptions, are not a bunch of basically are not just a bunch of assumptions to make, and then based on that we get a value. It's not like that. But once we basically once we define limits properly, then you'll see that basically this whole thing actually does make sense. Otherwise, I mean, it would actually be possible to define limits exactly at this point and get rid of this confusion, but you don't really need to worry about this thing, because basically in the next portion of this book, or the next book that we talk about limits and derivatives and integral and things like that, then hopefully over there we will define limits, and then we can take care of get rid of the confusion that you might have right now, because everything over here seems to be just like based on chance, or we are making assumptions that and there is no way to make these assumptions really. So but these will make sense in the future. And again, we made the same assumption over here, that for example the value of f of x at x is equal to 1 seems to be equal to 1 as dictated by these numbers. So we said that the limit of f of x as x tends to 1, as x tends to 1 from the right is equal to 1, and then we said that it's likely that the limit of f of x as x tends to 1 from the left is equal to the limit of f of x as x tends to 1 from the right, both of which are equal to 1, which we took as the limit of f of x as x tends to 1, and that is basically based on the definition of the limit. We said that if this limit exists, and if this limit exists, and if the value of both of them, the values of both of them are one exact same number, then we call that number the limit of x as x tends to a, for example. And so if you take a look at the and then of course you need to pay attention to the word somewhat. We said that this conclusion is somewhat strengthened by seeing the graph of the function, because again the graph of the function is it's not just this graph over here that you can see. It seems to be, I mean, this graph, if you do it properly, of course this is not a proper graph, but suppose that I enter f of x or y is equal to x cubed. Okay, so this would be the graph of the function f of x is equal to x cubed. Now, what happens here is that this seems to be a curved line, right? This graph over here, this seems to be a curved line. But in reality, this curved line is very, very tiny bits and pieces of lines, of straight line segments put together. And the reason why I'm saying that is that because as we probably, if you have understood what we said about the process of derivatives, we saw that the derivative of this, meaning that basically the slope of the tangent line at any point on this graph is going to be different, and it's going to be, for example, suppose that you have this graph over here. Suppose that you have this graph over here, and for example, let's say that this is your graph, and suppose that this is f of x is equal to x cubed. Okay, so this seems to be a curved line, basically a curved line, you could say, for example. But we said that based on what we said in the whole process of derivatives, what we found out was that, for example, from this point all the way up to this point, if we wanted to find the average velocity, this was the slope of the secant line. If it was from this point to this point, the slope of the secant line changed to for example this line, and so on and so forth. And when I got over here, exactly at this point, the slope of the secant line was slope of the line that was touching the graph, slightly touching the graph exactly at one point on that point. Touching the graph exactly at one point, and that point is basically that point over there. So then if I zoom in on this function and go in and go basically zoom in by a factor of, I don't know, by a large factor, and just keep going in and going in and going in, then of course this curved piece of line is going to be the sum total of all of these very tiny pieces of line segments, the slope of each of which is going to be equal to the slope of the slope of each of which is going to be equal to the slope of the tangent to the graph of the function at any point. Meaning that at this point, if the slope of the tangent to the graph of the function is this slope, whatever that might be, you can, if you zoom in on this graph and just keep going in and going in and going in and zooming in and zooming in, you will find that instead of a curved line, what you will find is just a piece of straight line, having a tiny piece of straight line segment, having exactly this slope over here. And then the next bit, of course, it's going to change. The slope is going to change, and all of these pieces of straight lines are just put together and then going to the right, to the left, to the right, to the left, and so on and so forth. And then when you look at the whole thing from very far behind, you will see a very seemingly smooth piece of curved line. Otherwise, if you go in, you will see this jagged piece of line. You see this jagged path that just keeps going to the right, jumping to the right, to the left, to the right, to the right, to the left. So, based on that, when you simply look at the graph of a function, you're not really seeing the graph of the function, because as you keep going in, then you might actually see that, for example, the graph of the function all of a sudden jumps up and jumps down, jumps up and jumps down. But when you look at the whole graph from far behind, meaning that if you zoom out, then of course you're not going to see those variations on the graph of the function, because now you're looking from far behind. You have zoomed out, and you will see a piece of curved piece of basically line, a smooth curve. You will see a smooth curve as the graph of the function. So what that means is that you cannot, so therefore we have used the word somewhat, and what that means is that somewhat meaning that you're just taking a look at the graph of the function. Otherwise, if you go in anything, if you zoomed in on the graph of the function at any point, or at any interval of the domain of the function, then you could see anything inside. It's not like, for example, you have a zoom factor 0, for example, and you will see basically this this smooth curve over here, and then when you zoom in, anything could be inside. Anything could be, anything could really come up as you zoom in and in and in and so on and so forth. So therefore we have used the word somewhat, is somewhat strengthened by seeing the graph of the function. But then of course, once we know more about how exactly basically these limits work, then you will know more about, basically you can make sure that these limits are actually going to work for you. Okay. Now the next thing that we have over here is another illustration, which is illustration number 3. For example, suppose that you have a function, for example, f of x is equal to 3 times x. So if you have f of x is equal to 3 times x, so first of all the graph of this function is going to be this graph over here, meaning that the function goes through 0, 0, and then the slope of this function is 3, meaning that you would get this line over here. Okay, so that is basically f of x is equal to 3x. Now what we want to do here is basically we want to find the limit of this function. We want to find the limit of f of x as x tends to 2. So if I prepare a table over here and put all of these values over here, for example, if I take this as x, and if I take this as f of x, and let's suppose that this point over here is x is equal to 2. And so of course I have to basically get closer to 2 from the right, and from the left to this function, in this function. So basically what I'm going to do is basically suppose that I take 2.001 for example, then I can have the point 2.01, then I can have the point 2.1, and then on the other side I can have 1.999, then I can have the point 1.99, then I can have the point, for example, 1.95, and then I can have the point 1.9. So the output of the function, for these inputs are going to be basically, for example, for 2.001 is going to be, for example, 6.003. For 2.01 the output is going to be 6.03. For 2.1 is going to be 6.3. For 1.999 the output is going to be 5.997. For 1.99 it's going to be 5.97, and for 1.95 it's going to be 5.85, and for 1.9 it's going to be 5.7. So as you can see, as I get closer to 2 from the right, basically as I get closer to 2 from the right, then you can see that the values are getting closer and closer to 6. As I get closer to 2 from the left, you can see that 1.9, 1.95, 1.99, 1.999, the values are getting closer and closer to 6. So as before, basically we observe that as x approaches 2 from either left or right, the value of f of x seems to approach 6. And so we can mathematically write this as the limit of f of x as x tends to 2 from the left, for example, is equal to the limit of f of x as x tends to 2 from the right is equal to the limit of f of x as x tends to 2 is equal to 6. And of course, if you go over here and take a look at the output of the function at 2, we'll get to this point, which is basically 1, 2, 3, 4. Of course, this is supposed to be 6, for example. 1, 2, 3, 4, 5, and 6. So this is 2, 6 over here. So, and basically, so you can see that the limit of the function as x tends to 2, the limit of f of x as x tends to 2 is equal to f of 2 is equal to 6. That is again the case over here. Now, if you want to get too technical about this, of course you would confuse yourself. You need to wait until we get to the proper definition of limits, and I advise you not to do that. I would advise you against doing that until we get to the proper point where we can properly define basically these limits. Okay, so now suppose that you have another function. Suppose that you have another function, f of x is equal to 3, for example. You have this function f of x is equal to 3. Now we want to find the limit of f of x. We want to find the limit of f of x as x tends to 2. Or basically, in other words, we want to find the limit of f of x at x is equal to 2. So since this is a constant function, you know that the constant function has the same value throughout the whole domain of the function, meaning that, for example, 1, 2, and 3, and then you would have x and y over here, and this is basically f of x is equal to 3. So it has the same value all throughout. Everywhere everywhere your y is equal to 3, y3, and so all the way from negative infinity to positive infinity. So that means that at any point, if this is basically x is equal to 2, if this is x is equal to 2, this point, at any point close, as you get closer and closer to 2 from the right or left, the value of the function is simply going to be 3 and not changing. So then you can say that the limit of f of x as x tends to 2, for example, from the right is equal to the limit of f of x as x tends to 2 from the left, is equal to the limit of f of x as x tends to 2 is equal to 3. And again, you can see that the limit of f of x as x tends to 2 is actually equal to f of 2, which is equal to 3. And so basically, since f of x is a constant function, then you can say that basically you saw that over here the limit of f of x as x tends to 2 is equal to f of 2 is equal to 3. But it applies to any point in the domain of the function because at any point the value of the function is, at any point in the domain of the function, the value of the function is actually the same value basically f of x. So what that means is that then you can write the limit of f of x for a constant function. The limit of if f of x is a constant function, then the limit of f of x as x tends to a is equal to f of a, and that is equal to f of x. That is for any basically constant function. Now you can, in this particular case, you can write the limit of f of x as x tends to a is equal to 3 basically. Is equal to 3. So that is that. Now let's suppose that we have another function f of x is equal to, for example, x squared plus x. F of x is equal to x squared plus x. Now we want to find the limit of f of x we want to find the limit of f of x at x is equal to 1, or we want to find the limit of f of x as x tends to 1. So in order to do that, first you need to basically find out what this function looks like, and in order to do that you need to basically do a couple of points on the graph of the function. For example, you could, if x is equal to 0, then of course f of x is equal to 0. If x is equal to 1, then f of x is equal to 2. If x is equal to negative 1, then you will get 1 minus 1, 0, negative 1, 0. If x is equal to negative 1, you will get negative 1 squared minus 1, which is equal to 1 minus 1 is equal to 0. It's weird. If x is equal to 2, if x is equal to 2, then f of 2 is equal to 4 plus 2 is equal to 6. 4 plus 2 is equal to 6. And let me take a look at the graph of this function. X squared plus x. I see. Okay. Okay, so basically between, you see that the function goes through the x-axis at these 2 points, at x is equal to 0 and at x is equal to negative 1. So that means that somewhere between, or exactly between these 2 points, the graph of the function, basically you will have the vertex of the parabola. So at x is equal to 0.5 or 1/2, as x is equal to 1/2, you will get 1/2 squared plus 1/2, which is equal to 1/4 plus 1/2, which is equal to 4 1/3/4, which is equal to 3/4. So at x is equal to 1/2, you're at 3/4, somewhere negative 1/2 actually. At negative 1/2, at x is equal to negative 1/2, you're at 1/4 minus 1/2, which is equal to 4 1 minus 2 negative 1/4. Negative 1/4 would be some point over here. So then the graph of the function is going to be something like this. I could basically do a couple of points over here, and then the function is going to be symmetric about this line. About this line, which is x is equal to negative 1/2. So the function is going to be symmetric about this point. Okay. Now that is basically your function. Now, what you want to do here is basically find the limit of the function at x is equal to 1, which we found to be basically the value of the function at x is equal to 1 is 2. So that is 1 comma 2. So as you can see, as I get closer and closer to 1 from the right and from the left, the function is tending towards this point 1 comma 2. That means that you can simply say that the limit of f of x when x tends to 1 from the right is equal to the limit of f of x when x tends to 1 from the left is equal to the limit of f of x when x tends to 1, which is equal to 2. and so now here you observe that, so here again we can see that the limit of f of x as x tends to x tends to 1, for example, is equal to f of 1 is equal to 2. That is basically, again, I mean, this is what we have seen in almost all of the examples that we have done. So what that means is that there are a couple of things here that we can observe in this example. Now you can see that the limit of x squared, you can see that the limit of x squared, if x tends to 1, for example, is equal to basically 2. The limit of x squared when x tends to 1 is equal to 1. Is equal to 1. The limit of x squared when x tends to 1 is equal to 1. And the limit of x when x tends to 1, so that would again be equal to 1, because you would have basically this function over here, something like this, or exactly this function, and then you would have this point on the graph of the function. This is 1, 1, and so the function would tend towards this point, and so the limit of f of x, which is now in this case is equal to x, when x tends to 1 is equal to 1. And the limit of x plus 1 and also the limit of x plus 1 when x tends to 1, is equal to, well, this is a function. If you set basically 1 plus 1, that's going to give you a 2, because this is a function something like this, and then having this kind of slope, and then the function will go through this point and this point over here. So this is going to be that. So the limit of x plus 1 as x tends to 1 is equal to 2. So now what happens here is that you can see that the limit of x squared plus the limit of x, again as x tends to 1 over here, as x tends to 1, is equal to 1 plus 1. X squared plus x is equal to 1 plus 1 is equal to 2, and that is equal to the limit of x squared plus x as x tends to 1, because the limit of x squared as x tends to 1, here we found that to be 2. And of course these are this is no proof, this is just some relationship that we have found between all of these things over here. And also the limit of x squared as x tends to 1 times the limit of x plus 1 as x tends to 1 is equal to the limit of x squared as x tends to 1 is equal to 1. The limit of x plus 1 as x tends to 1 is equal to 2. And that is actually equal to the limit of basically x squared times x plus 1. I made a mistake here, I'm sorry. The limit of x actually, so it doesn't make any sense this way. So the limit of x as x tends to 1 is equal to 1. The limit of x plus 1 as x is equal to 1 is equal to 2. So 1 times 2 is equal to 2. Okay. Now, this is actually equal to the limit of x times x plus 1, x times x plus 1 as x tends to 1, because you can rewrite this as the limit of x squared plus x as x tends to 1, which we found over here to be equal to 2. This function over here was the limit of x squared plus x, and we found the limit to be 2. So then you can say that, basically in short, you can say that basically the limit of x squared plus the limit of x, in both cases as x tends to 1, is equal to the limit of x squared plus x as x tends to 1. And the limit of x times the limit of x plus 1 as x tends to 1 is equal to the limit of x times x plus 1 is equal to the limit of x squared plus x as x tends to 1. So that's basically something that we will take advantage of in the algebra of limits. Okay, so I think it's enough for this video. We will continue the rest in the next video.